Hello, chemistry students. Over the last 2 weeks, we have been looking at stoichiometry, which has to do with the ratio that these atoms and these molecules reacted. And so we've seen mole to mole stoichiometry, we've seen mass to mole stoichiometry, we've seen mass to mass stoichiometry, and this is the last concept of this unit. This is the limiting reactant. What we are going to look at is the concept of it. We're not going to do a ton of questions with it. If this was an honors chemistry class, AP chemistry, absolutely. We're doing a lot of mathematical questions with the limiting reactant. But for us, in just this whole crazy time, we just want to get the concept of the limiting reactant down. So that's what we're really looking at in this video, and I'll show you a couple of tricks. All right, so the definition. The limiting reactant is the reactant that limits the amount of the other reactant that can combine and the amount of product that can form in a chemical reaction. All right, now the other important term to know is excess. The excess reactant is the substance that is not used up completely in a reaction. So down here, we have a reaction of carbon and oxygen forming carbon dioxide. All right, the green, the carbon we see getting used up, right? All of the carbons have formed carbon dioxides. Carbon is the limiting reactant, all right? It was used up and it limits the amount of product. We have 5 carbons, we make 5 carbon dioxides. We had 10 oxygen molecules, all right? And we have 5 oxygen molecules left over as excess, all right? You may have noticed in a lot of the questions we've done, I've used that term excess, all right? So you didn't even have to worry about the limiting reactant. I was telling it to you technically. So you've actually been using the limiting reactant in all of the stoichiometry problems I've given you. You just didn't know you were using it yet. All right, but it's still a little weird. So if we were in school, this is a video that I always love to show. So we're just gonna sit here and watch it for a second.
Ina said as long as I was escaping, would I mind escaping to the market and picking up something
So
for dinner?
this is from
Sure,
the movie Father of the Bride.
Supermarket. I needed to drive.
All right, it's
to
an old
mellow
movie,
out, get my
comedy,
mind off the
very
wedding.
good. Before The Office existed.
But mellowing out was not in the cards.
So Steve Martin, he's the father of the bride. He's very tense, and he's in the grocery store right now.
Excuse me, sir. What are you doing? I'll tell you what I'm doing. I want to buy 8 hot dogs and 8 hot dog buns to go with them. But no one sells 8 hot dog buns. They only sell 12 hot dog buns. So I end up paying for 4 buns I don't need. So I am removing the superfluous buns. I'm sorry,
Right.
sir, but
8 hot dogs, 12 buns, excess buns.
Yeah. You want to know why? Because some big shot over at the Wiener Company got together with some big shot over at the Bun Company and decided to rip off the American public because they think the American public is a bunch of trusting nitwits who'll pay for things they don't need rather than make us stink.
He doesn't want to pay for things he doesn't need. That is fueled by the wedding. I get that. Having been married myself, going through that process is stressful.
Who's George Banks?
Great actor.
Why don't we just calm down now, sir? I'll tell you why we don't calm down. Because you're not excited. It takes 2 people for a we to calm down, doesn't it? That I don't know, sir. I'm just the assistant manager of a supermarket. But I'll tell you this. If you don't pipe down and pay for those buns, I'm going to call the police. Oh, right. Yeah. Yeah, right. That's right. Hey, right. Hey, come here. Come here. Come here.
All right, so he's been upset about the hot dogs and the buns, and now he's in prison. This is a great movie, Father of the Bride. Check it out. All right, and it seems laughable, but it is true. All right, so here we have a 8-pack of hot dogs, but look at this package of hot dogs. Take a second. Count how many hot dogs are there. All right, 7. So what are you supposed to do? All right, so now you're going to have your pack of 8 buns and your 7 hot dogs. So now you need to buy a second thing of hot dogs. So now you have that 8th hot dog for the bun, but now you have 6 hot dogs left over. So you have to buy another thing of buns for those 6 hot dogs to go in. So now they go into 6 buns. But you have 2 buns left over. So then you buy another thing of hot dogs. Now you have 5 hot dogs left over. So now you buy another thing of buns. Now you have 3 buns left over. So you buy another thing of hot dogs. Now you have 4 hot dogs left over. So you buy another thing of buns. But now you have 4 buns left over. So you buy another thing of hot dogs. It goes back and forth until you reach a common denominator. You have to have 56 hot dogs. All right, you got to buy 8 packages of the 7 hot dog wiener packages, and you have to buy 7 packages of the 8 buns, right, to get 56 individual hot dogs to get the perfect stoichiometric ratio. Now you're probably saying, well, Mr. L, all right, chemistry is tough. I'm doing my best here. I'm sitting here watching your video, but I don't know what's going on. All right, I'm just gonna buy the hot dogs. I'm gonna buy the buns. I'm gonna have 7 hot dogs, and that 8th bun, I'm gonna feed it to a duck, because theoretically, I'm grilling the hot dogs in a park, because we're allowed to be in a park right now. All right, and that's fair. I get that, but I just want you to be aware. For the most part, you go to the grocery store, you're gonna get 8 and 8. But this situation really shows us the limiting reactant really well, right? Something gets used up once you've placed all 7 of those hot dogs. It's gone, right? It's used up, and you're standing there holding that 8th bun in your hand. That's the excess. All right. So I just want to do another analogy. I want to think about a manufacturer. All right. A manufacturer that's making cars. Right. They have to order the frames and the tires. All right. Now we know the cars. I mean, I don't know what kind of cars you're driving around in, but mine has 4 wheels. All right. So we need 1 frame. We need 4 wheels, right? That's the ratio. That's the stoichiometric ratio, right? For every 1 frame, you need the 4 wheels. All right, that's how it comes together at its simplest level. Right, so 1 frame, 4 wheels. So that's the ratio, 1 to 4. That's the perfect ratio. Now let's say we get 1,000 of each. We get 1,000 frames at the manufacturer. We get 1,000 wheels. Well, how many cars are we going to be able to put together? All right, so for every 1 frame, you're using 4 wheels. All right, if we just divide 1,000 by 4, right, we're going to get 250. So we can make 250 cars with those 1,000 wheels, right? That's the total amount of cars we could make just based on the wheel, 250. If we think about the frame, you only need 1 frame per car. All right, so if we do 1,000 and we divide by 1, we could theoretically make 1,000 cars, but we would need enough wheels. So since we're gonna run out of wheels after we make 250 cars, right? Production's gonna stop. We don't have any more wheels. So what we're gonna end up making is 250 cars, and we're gonna have an excess of 750 frames, right? They don't have wheels, so they're useless to us. All right. Now, what if we had 1,000 frames and 5,000 wheels? All right. Well, now, if we have 1,000 frames, we could make 1,000 cars. Now, how many wheels would we need to make 1,000 cars? We would need 4,000 wheels. How many wheels do we actually have? 5,000. So now it's kind of like we flipped the switch on this, right? Now the frame is the limiting reactant in this given amount, right? We're going to run out of frames when we use 4,000 wheels, but now we're going to have 1,000 wheels left over. So in theory, we could call someone up and order 250 more frames to go with those wheels, right? Or maybe we can give everyone a spare tire, a full spare. That'd be nice, right? But the idea is you want to think about the simplest ratio, all right? Hot dogs and the buns, that should make sense to you guys. Car frames and wheels, that kind of makes sense. I know that might be a little bit of a stretch. Now, I get that when we come to molecules of compounds, and individual atoms, now we're in a realm that we're not as comfortable with. But the logic is the same, all right? The important thing is stoichiometry is happening at the atom level, right? So 2 molecules of hydrogen with 1 molecule of oxygen are forming 2 molecules of water, right? That's the ratio that these tiny, 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 tiny individual atoms are reacting in. All right. Now, we are allowed to scale it up. So let's say I take my hydrogen and I multiply it by 6.022 times 10 to the 23rd, Avogadro's number. right? I am allowed to work with moles. So that is allowed. We can work with moles, right? We've been doing the mole ratio, so that's totally fair. We can't use mass. We can say 2 moles of hydrogen plus 1 mole of oxygen makes 2 moles of water. We cannot say 2 grams of hydrogen plus 1 gram of oxygen. That's completely wrong, right? Cannot use mass. That's why we had to divide by the molar mass in our mass to mass problems from last week, right? Cannot use mass, only moles here. But I want to look at something. Let's look at this setup, right? Let's remember our reaction. 2 hydrogens plus 1 oxygen forms 2 waters. All right, we're told we have 10 hydrogen and 7 oxygen. Okay, now obviously we have the answer here, but I just want to think, how can we come up with the limiting reactant? All right, because it's a 2-to-1 ratio, right? We need twice as much hydrogen. Now, if we have 10 hydrogens, half as many hydrogens would be 5, right? For 10 hydrogens, we need 5 oxygens, and we're told we have 7, right? So we have all of the oxygen to react with all the hydrogen and a little bit of extra. So the hydrogen is the limiting reactant. The oxygen is the excess, and we're going to have excess oxygen. We can see, because we have a particle diagram here, right? The red represents the oxygen, the white is the hydrogen. They come together to make these water molecules, but the leftover oxygen, it's still there. It has no one to react with. All right, so the trick, this is the tip that I'm going to show you. We're going to do a practice question with it. All right, how do I determine my limiting reactant? I kind of get the idea of these ratios, but it's a little tricky for me. All right, you want everything to be in moles. Right, I'm going to be nice to you. I'm going to leave everything in moles, but if you ever find yourself in a situation later down the road and they give you grams, you're going to divide by the molar mass, but you're going to get moles from me. All right, so we have 10 moles of nitrogen, 10 moles of hydrogen. You always take your moles and you divide it by the coefficient, right? It's always going to be reactants, right? Limiting reactant. We're not worrying about the products, limiting reactant. So you're going to take your moles for each reactant, you're going to divide it by the coefficient, and whichever number is smaller, that's your limiting reactant, right? The smaller number is the one that's going to be used up first. The reason why we're dividing by the coefficient, right, is because we want it in a 1-to-1 ratio, right? Hot dog plus hot dog bun, that is easy. You got 7 of one, 8 of the other. You know the 7 is the limiting reactant. But when you get these more complicated ratios, 2 to 3, 3 to 5, things like that, now we got to do a little more of that math. So when you divide by the coefficient from the balanced reaction, when you divide by the coefficient, you make it a 1-to-1 ratio. All right, you're not going to use this number for anything else. It's just going to be to identify the limiting reactant. All right, so here, 10 moles of nitrogen divided by a coefficient of 1 gives me 10. 10 moles of hydrogen divided by a coefficient of 3 gives me 3.33. 3.33. Hydrogen is less than 10. 3.33 is my limiting reactant for this problem. All right, so now here is another example. We have the reaction, it's balanced, right? We're given the reaction zinc plus 2 AgCl yields 2 Ag plus ZnCl2, okay? Pure zinc plus silver chloride yields pure silver plus zinc chloride, right? If I have 3.5 moles of silver chloride and 2.8 moles of zinc, which substance is the limiting reactant? Do you know the answer off the top of your head? Maybe this is all clicking and you got that, all right? But these numbers, they're kind of close to each other. I know that I need more silver chloride, right? Because it's a 2-to-1 ratio, and I do have more, but do I have enough? So here's what we're gonna do. We're gonna write out, right? 3.5 moles AgCl, 2.8 moles Zn. We need it in moles, it's in moles, we're good to go. Remember, I am going to give you everything in moles for limiting reactants. You don't have to worry about that. We're gonna divide by their coefficients. All right, the AgCl's coefficient is a 2, so we're dividing by 2, 3.5 divided by 2. And for the Zn, its coefficient, there's no coefficient listed, that means it's 1, right? We're dividing by 1. So we get 1.75 for the AgCl, we get 2.8 for the zinc, and what's the question we ask ourselves here? Which number is smaller? All right, obviously the 1.75. So that is our limiting reactant. All right, the AgCl would be the limiting reactant based on these amounts. All right, so that is the concept of the limiting reactant. All right, now remember, um, in an honors chemistry class, in an AP chemistry class, right? We are going to be doing mass to mass stoichiometry problems with limiting reactants. You're going to have to find it. You're going to then have to take that number. You're going to have to go back. You're going to have to solve the whole thing, right? It's going to get bigger. It can be very daunting. That is not what we are doing this year in our CP class, right? We just want to appreciate that one of the compounds runs out. And when it runs out, the reaction stops, right? We don't make any more product. We can do a lot of stoichiometry to figure out how much product we make, things like that, all right? But we're gonna save that for the stoichiometry problems we've already practiced, and for limiting reactant, we just wanna use this trick. Take the moles, divide by the coefficients. The smaller number is the limiting reactant, and the bigger number automatically is your excess, all right? So that's the concept of the limiting reactant.